In this video, we'll discuss conditional expressions in Scheme, starting with the if expression. So the syntax for an if is as follows. We have some combination set in parentheses here, where the first term is the keyword if. Following that, we have some condition, or the antecedent. Then we have the then expression, or the consequent, which is the thing that gets evaluated if that condition is true. And then we have some other expression here that's called the alternate, which is what gets evaluated if the condition is false. So let's start with a simple example here. Define a function max. So define max between two values x and y as if x is greater than or equal to y, so greater than or equal to xy, then we'll return x, otherwise we'll return y. So if x is bigger, we'll return x. If it's equal, we'll return x, otherwise we'll return y. And either way, you'll get the largest value coming out of this function. So let's run this. And we get max. Let's just take two values, 1 and 10, and the answer is 10. Good. If you get an error running this code, because if it says something along the lines of max is already defined or can't be redefined, make sure you have R5RS custom as your language. You'll see in a previous video the option for setting that correctly. So a bit about the semantics of the if expression in Scheme. Now I say if expression because it does in fact have a value. And the value of this if expression is the result of whichever branch gets evaluated. So the alternate or the consequent, that's the then part or the else part. The value of one of those expressions becomes the value of the entire expression. So we could say something like define x to be if, and I'll say if false for an easy one, 1, 2. So a real simple if statement, or a real simple if expression. So in this case, because this is false, it will evaluate this branch here. The value of that is 2, so the value of the entire if statement is 2, and so x now has the value 2. Okay. Secondly, about if statements is the notion of truthiness, which is to say anything that is not specifically false, that is, say, the hashtag F symbol, is considered to be true. What this means is if we have weird if statements, maybe something looks like if 1, 2, 3, this is a valid if statement. And its value will be, so first it considers what is the value of the condition here. Because it's not specifically false, we consider it to be true, and so we'll evaluate the true branch, the then parameter. And we get 2. Similarly, we could say if 0, 2, 3. And in some languages, using a 0 as an integer instead of some Boolean value is considered the false version of an integer. In Scheme, anything that is not specifically false is considered true, even zeros, empty strings, all those things. So long as they're not specifically false, we get true. Right? If I say if the plus symbol 2, 3, the plus symbol isn't false, so it's considered true, and again we get the value 2. If I had said if specifically false 2, 3, then it says, well, we'll evaluate the else part and get 3. Okay, so anything that's not explicitly false is considered true in Scheme. Okay, and thirdly, the if expression is a special form. Now, we've already seen what special forms are. Special form means that it doesn't follow the usual applicative order. So it doesn't evaluate all of the sub-expressions before applying the function, in this case would be some sort of if function, to its arguments, which would be the remaining symbols, the remaining sub-expressions. So in almost all eager languages, if statements are still evaluated lazily, which is to say, rather than evaluating all of the parts of the if statement, as we would in normal applicative order, sorry, I should say usual applicative order, other than evaluating all of the parts, it will evaluate specific parts. And this is a very important element. It'll become very important when we start making recursive functions later on. So the specifics of how Scheme evaluates if expressions is as follows. So first off, sees the keyword if, and we can see that that's not a function, because if we ask what's the value of if, it says bad syntax. And this happens specifically when we have special forms here. So if has some sort of special meaning to the Scheme interpreter, and it's not going to use the regular eval apply loop. Instead, what it will do is it will take these three sub-expressions, the condition, the then part, and the else part, and it will say, first off, evaluate the condition, determine does this thing boil down to true or false. So it doesn't have to be specifically false in this place. It could be some sort of expression that evaluates to false or an expression that evaluates to true. Either way, we'll get some sort of value out of that expression. If the value of that expression is specifically false, then it will evaluate the else part. If it's anything but false, it will evaluate the true part. Okay? But never both. It won't evaluate both the then and the else part. It will evaluate one or the other and return that as the value of the entire if expression. Okay, so for example, I could say something like, if true, 1, else, and then just use some sort of bad variable. So bad variable doesn't exist, so if we tried to evaluate this expression, Scheme will crash saying the variable doesn't exist, so it's a naming conflict. And in this case, because our condition is true, we're only going to evaluate the then part, the consequent. So if we run this, no problems. Now if I were to run this with #f instead, notice the whole code crashes because as soon as it attempts to evaluate this variable, it can't and it crashes. So again, if this were using applicative order, we'd evaluate each one of these sub-expressions and then apply some sort of if function onto the values of its arguments. But that's not what happens. If is a special form, it has its own rules of evaluation. It says evaluate the condition, and then depending on that, evaluate one or the other of the two branches, but never both. All right. Now we're talking about conditional expressions. It's important to remember all the basic Boolean operations that are available. I believe we covered all of these in previous videos, but here they are in the notes. So you have all the different relational operators, less than, greater than or equal to, equal to. Notice there is no not equal to in Scheme. So if you want to say not equals, you can just use an equal sign and the negation operator not. We also saw and, or, and not in the previous video, so I'm not going to belabor those points, but here they are again for your reference. There's also a bunch of built-in predicate functions, some of which we've seen before. We saw the different type checking predicates, number, integer, string. There's others for lists and symbols and other types of data that we'll see later on. But there's other built-in predicates for other useful operations or other useful questions to ask of our data, like is a number even, is it odd, is it positive? There's many others out there. I'll leave you to the internet to find them if you need them. Okay, one thing to mention, I believe I mentioned it before, but just in case I'll say it again, when you're creating predicate functions or if you're finding built-in predicate functions, the convention is to always end them with a question mark. This just tells the user of that function this thing returns true or false. Nothing else, just one of those two values. All right, I think we covered all that. Let's do a simple example here. So I'm going to create a function. Where's my code? Here it is. Define, let's say, example x, y, z. And this function is going to take in a bunch of information. It's going to have, double bracket, if x is greater than 5 plus times, and if y is less than 10, yz, and if and x is less than y, and z is less than y, then y minus x, otherwise times xz. So, it's a bit of a nonsensical function, but it uses a bunch of if statements in some strange ways that we'll have to walk through to try and understand. But before I do the walkthrough in the video, I recommend pausing the video now and try and figure out what you expect the output of this function to be if I were to run it with 10, 2, and 3 as arguments. So pause the video now, see if you can figure out the walkthrough of this code, what the output should be, without just running it, obviously. And then we'll walk through and see if we can't understand it as well. All right, welcome back. Let's go to understanding this code now. So let's start with a substitution model. Actually, before I get to substitution model, I want to just walk through the general structure here because there's a bit of an odd structure. First off, we have a double bracket, which you don't see a lot in Scheme because typically speaking, when you have an open parenthesis, the next thing needs to be some sort of operation, right? We're creating a combination where the first thing is the operator and the remaining things are the arguments or the operands. In this case, though, the first element in this combination is itself a combination, an if expression to be specific. But what that means is, in order for this outer combination to be valid, and that outer combination spans the entire body of this example, but in order for that outer combination to be valid, the value of the first symbol in that combination needs to be some sort of procedure object. So let's look at this if statement real quick. So it says if x is greater than 5, and then the then part, or the consequent, is plus, and the else part here is times. And we know the values of those two expressions, right? So we know the semantics say if this is true, it will evaluate this symbol. If it's false, it'll evaluate that symbol. And if we evaluate those symbols, we've done this before, we can see we have either the procedure plus or the procedure times, respectively. So what comes out of this if statement is going to be a procedure object. And that will then be the first element in a combination where the remaining if statements here will determine the arguments to that object. Now, if that doesn't make sense, let's walk through a substitution model. Substitution model. Okay, so our first line here was the line that we typed in there, example 10 to 3. Now, if I don't specify in a video or on an assignment or on a test, if I say let's do a substitution model and I don't specify a specific evaluation strategy, then assume the default, which is applicative order in Scheme. Now, applicative order says evaluate all of the sub-expressions, one at a time, before applying the value of the function to the value of its arguments. Now, if we evaluate example, we'll get the procedure that represents this function that we defined from lines 4 to 9. If we evaluate 10, 2, and 3, those are self-evaluating because they're integers, so we'll get 10, 2, and 3. So pretty much everything's as simple as it can be, and we're ready to apply. So the apply step says take the values of these arguments and substitute them into the parameter symbols throughout the body of the function. So this is going to get a little bit messy. We want one fewer bracket because we're not taking the define line. It's going to get a bit messy because with the substitution model, we typically draw them on a single line just to keep track of the order of operation. When we're creating functions in actual code, we tend to condense them over multiple lines just because they're easier to read. So what we're going to do is put this all on one line and then just be very careful what we delete if we need to delete things. Copy and paste is going to be our friend here. So we've taken the body of example. Now the substitution step says we take in 10 for x, 2 for y, and 3 for z. So anywhere we see an x, we'll make it 10. We see a y, make it a 2. Anywhere there's a, we'll make it 3. 10, 2, 3. Oops. 2, 2, 10, 10, and 3. Okay, so with that substituted into place, we can now walk through evaluating the body of this function. Now the body of this function is one big combination with many sub-expressions inside, so we need to evaluate those sub-expressions before we can figure out the value of the overall combination. So the first sub-expression is what I have highlighted here. If 10 is greater than 5 plus otherwise times. So the semantics for an if statement say first evaluate the condition. So we have 10 is greater than 5. That evaluates to true. And our if statement looks like that for the rest of it. I'm just going to take the remaining line here because we're not changing that yet. We're going to go through this at a bit of a slower pace. I'll talk about shortcutting this at the end here. But just to make sure we have all the steps and we understand the order of operations here, let's go through it slowly the first time. So the condition here is true, so we have if true plus times, and we know that the semantics for an if statement say if the condition is true, we evaluate the third sub-expression, if you will call it that. In this case, the plus symbol. And we've already seen if we evaluate the plus symbol, we get procedure plus. I'm not going to bother typing out procedure plus every time. We can just remember that the plus symbol refers to the object in this case. So this whole expression, this whole if expression here, reduces down to the value of the branch that was evaluated, which in this case is the procedure for addition. Okay, and then we move on to evaluating the second sub-expression. So let's take the rest of this line, copy, and paste. Okay, so that goes through the same way. It says, what is the value of the condition? 2 is less than 10. That's hashtag true. So we can take that and use that to say, if this is true, we evaluate the then part of our if statement. So that whole thing boils down to a 2. And then we evaluate the next sub-expression, or the last sub-expression of the overall thing. And that's a bit of a big if statement. So we'll walk through that piece by piece. So if statement here has one big condition that's and two different comparisons. So an and is true if its first argument is true and its second argument is true. Yeah, so 10 is less than 2, that's false. I'll go down to the next step for the next line for the next step here. And we saw in the previous video that if the way AND works is also a special form. It's a special form for the sake of efficiency in this case, where we say false and anything is going to be false, so we don't need to evaluate this second step. We already know the entire condition will be false. So it's a short circuit operation, and as soon as we have one false, the whole thing must be false, and we can just jump to that answer. Okay. Now, because our condition is false, the if statement says evaluate the last sub-expression. In this case here, times 10(3). So the entire if statement gets replaced. Delete that and one of the brackets. The entire if statement gets replaced by the body, or sorry, the branch that would be evaluated. Okay. And then it's just reduce things. So times 10(3) becomes 30, and 30 plus 2 is 32. Okay. And if we're not sure that worked, let's just let's just uncomment everything, as we saw when we were learning about substitution models. Every single one of these lines is saying the exact same thing, just in various forms of completion. And if we scroll up, we should get all 32s, and that's what we have here. Good. I recommend leaving them commented out in your final submission. That way it doesn't spam your output. So that's the if statement. Now, as I mentioned before, it's a bit exhaustive to do it this way. If you want to evaluate an if statement by one step evaluating the condition, and then in the next step determining what the actual branch is, rather than taking essentially 3 steps to figure out an if statement each time, we can do that all in one step. Something along the lines of, here, I'll just take this. Yeah, go from about here. I'll just do the first step here. So we did the substitution. We called example with 10, 2, and 3, and we took the body of example where x is 10, y is 2, and z was 3. And then it said evaluate this if statement. Now, as humans, we can pretty quickly evaluate this if statement. The computer can do it too, so we're not helping anybody by belaboring the point beyond the first time just to see it. So in this case, we can see that this is going to be true, so we can just jump straight to the active branch. So it'll be something along the lines of, from this whole if statement, we just know it's going to be plus, and then we have plus. Now, if this were some sort of combination, like 10 times 10(3), for example, we do the same thing. The if statement would boil down to the active branch, the entire expression, unevaluated, and then throughout the substitution model, we'd evaluate it line by line. Because that might be a very complex thing, like a function call or a very deeply nested arithmetic expression, it's useful to just take the whole branch as it is, cut and paste it in place of the if statement on the following lines, so the entire if statement gets replaced by the effective branch there, and then you can continue evaluating using the normal rules. Okay. All right, so I think that's if statements in a nutshell. Yeah. So let's move on now to the cond expression. So if statements are all well and good. Before we get to the cond expression, though, let's just cover this working example here. So the signum function is a piecewise function that's defined as follows. So given some number x, doesn't have to be an integer specifically, any number x, if it's a positive number, signum returns 1. If it's a negative number, signum returns -1. Otherwise, it returns 0. So it's a piecewise function with 3 possible branches. We can solve this using if statements if we want. We can say define signum of x, and I think it's right there in the notes, but it's good practice to type things out. So if we can solve this using if statements just by adding nested if statements. So I could say if, I'll start with positive, x is greater than 0, then return 1. But otherwise, in the else case, we need another if, because there's more questions. If it's not positive, it might be negative, or it might be 0. So one more question to distinguish that. We could say if x is less than 0, then -1, otherwise return 0. And if we run this code, we can ask signum of 3 gives us 1, signum of -3, and signum of 0. So it appears to work in all 3 branches. That's all well and good, but as you can imagine, if you have a very complex piece of code that has, let's say, 10 branches or 100 branches, it can be very convoluted to have to nest these things. And as the indentation grows larger, you're running out of space to type these things, so it's kind of a pain in the butt to have to use nested if statements all the way down. To that end, Scheme provides the cond expression, which is sort of a pretty printed nested if statement. So the cond expression has syntax that looks like this. The keyword cond, and then a sequence of pairs where the first element in that pair is some condition, so something that's true or false, or an expression that evaluates to true or false. And then some expression that represents the branch to be evaluated if that condition is true. Yeah. So the way cond works is essentially it will work down this list of pairs one at a time, starting with the first one, and say, if this condition is true, then I'll evaluate this expression. If it's not true, if it's false, then I'll move on to the next expression, or the next condition. If that's false, I'll move on to the next one, the next one, the next one, eventually finding one that is true and evaluating that expression. If all of them are false, well, we'll talk about that in just a minute. But first, let's see signum using cond, which again is right there in the notes, but let's type it for fun. So define, call it signum2 to prevent confusion, signum2 of x, and now we'll have a cond. So the cond syntax is a little bit strange here because each one of these pairs is wrapped in its own set of brackets, and then the pairs themselves need to be filled in with a condition and an expression, which require their own brackets. So the condition here would be greater than x0, and in that case we'll return 1. We'll have less than x0, we'll return -1, or we'll have equal to x0, and we'll return 0. So notice for the cond, we have essentially a double set of brackets around each one of these pairs, which is your first clue that cond doesn't follow applicative order, right? Because when we have brackets in applicative order that says take this function and apply it to this argument, but we can already see this thing is not going to return a function. It's definitely going to return true or false, assuming x exists. Anything else I need to say about cond before we get to it? No, I think that's good. Let's do a substitution model for this, and then we'll talk about the semantics a little bit. Okay, so first off, a substitution model, and we'll do signum -3. So again, with the substitution model, because this is just a function we created, we evaluate the two sub-expressions. This one here has the value of the procedure. If we run this here, call it signum2, sorry. We run this and we say, what is the value of signum2? It's the procedure that we happen to call signum2. So it's this thing here. Okay, and the value of -3 is just -3, so that's done as well. Okay, so the next step then is to apply this function to this argument, the values of each. So then the body of signum2 is a big old cond expression. And again, we'll put all this on one line, which will make it harder to read. Substitution models are good for some things and less good for others. It will help us understand the steps, though. So we have this cond, which is the body of signum2, where the argument -3 is placed in place, or substituted in place, for all of the x's. Okay. And then we walk through cond using cond's special rules. So the special rules for cond, again, as I mentioned, are we start at the first set of, the first pair, we can call them, and evaluate that first condition. If this thing is true, then we'll evaluate this branch. If it's false, then we'll move on to the next condition. So the next line looks exactly the same, except now we've evaluated this condition. So -3 is greater than 0. That's false, so it becomes #F. Then again, we move on to the next line, so copy this. And the next step says evaluate the second condition. -3 is less than 0. Well, that's #true. So the next line, we have our answer. Oh, we don't actually need to copy and paste that. So the next line says evaluate this sub-expression, but this sub-expression is just -1. It's self-evaluating, so we have our answer. Now, again, like with if statements, evaluating every single branch of a cond or each individual condition of a cond is a bit exhaustive, and it's not super informative in the long run once you start to understand this code inherently. So what you can do with these substitution models is, again, like with your if statement, you can go from the entire expression down to just the active branch. So we'd have signum2 of -3, then we'd have this whole cond expression. I'm not going to type it a second time. There we go, this whole cond expression, and then we just walk through manually and say, okay, well, this branch is true, or sorry, this branch is false, so we're not going to use that. This is the true branch, so this will be the expression that we'll replace it with. And again, if that were a larger expression, like maybe another function call or some large arithmetic expression, then we'd have in here, times 3 plus 2, 5, or whatever the value that was here. But because that's just a -1, we just put -1 in this case. Normally we still have to evaluate that, but because it's an integer, that's the last step and we're done. All right. So as I mentioned, cond is a special form. It has its own evaluation order. It does not just follow along the default rules. It can't just evaluate all of these combinations at the outset because, again, if we want to have recursive functions in here, that's going to be a real problem, as you'll see later on in the course. So it evaluates the first predicate. If it's true, it evaluates then just that one branch. If it's false, it moves on to the next branch until it finds one that is true. So it's different than the standard eval-apply process. And again, another simple way to check. Type in the name of the quote-unquote function to see if it has one of these backup procedure objects. If it's not stored that way, well, it's a slightly different one, then it's not a regular function. So it can't be handled in the regular eval-apply steps because it's not a function. This thing, by the way, is just Scheme's pretty printing way of telling you that there's a procedure object, some sort of information stored and bound to this symbol. Whereas the cond is not bound to some sort of procedure object, it's instead a directive to the interpreter itself to handle this in a different way. All right. So one last thing I want to say about conditionals in Scheme. It's kind of the difference between these two. So we've seen if statements, we've seen conditionals. We've also seen examples where both of them work together. Sorry, before I get ahead of myself. So one other thing I want to say about cons, and I alluded to earlier, and that's what happens if all the branches are false. So cons are, in fact, values. I can say define x to be the result. Actually, hang on a second, let's clean up the console here. Okay, we can say define x to be the result of some really simple cond. I'll say cond, and the first branch is a true, and it has the value 3. So a real simple cond expression, kind of a meaningless example, but just to show you that cond does have value, and like an if statement, its value is the value of whichever branch gets evaluated. Okay. Now, what happens if none of our branches are true? So we can say something like define y to be cond false. So we have one branch and it happens to be false, so none of these things are there. We ask what's the value of y, and notice it didn't print out a value. Notice it didn't also complain. It didn't say, well, that variable doesn't exist. The variable does exist. Scheme created essentially an empty binding for it. It knows this symbol, but it doesn't have a value associated with that symbol. So if you try using it, for example, in terms of arithmetic or something like that, it's going to crash saying this thing has essentially a null type value. The behavior of a cond where all the branches are false is undefined in Scheme's definition. So different implementations of Scheme will have different results, perhaps returning a null value or perhaps throwing an error. So it's a good idea to not ever leave a cond that could possibly have all of the branches empty. If you want to have a default branch, real simple alternative, we have cond here. We could say cond. Do I have an example of a cond to use for this? Nope. Awesome. You know what? I'll just copy this one here. Make a signum 3. So signum 3, if x is not positive and it's not negative, then it has to be 0. We don't have to ask this condition. So a real simple way to have a default branch is just say true at the bottom here. You say hashtag true at the end, then that's always going to be true, and there's your default value. If you don't like that, if that looks ugly to you, the normal way of doing it is to use the keyword else. Now, else is just part of the cond statement. It doesn't exist outside of that. So if you try asking what's the value of else, it doesn't have a value. But the cond special form knows if there's the else keyword, that essentially is a stand-in for the keyword true. And if it makes it to there, so if all of the preceding conditions are false, then it will evaluate the associated expression there, in this case 0. Okay, so keyword else, make sure you use that. It's quite useful in terms of creating cons that don't have non-values, so that do always have a value. Okay, now back to the one last thing I want to mention about conditional expressions, and that is essentially the difference between cond and if. So Pretty much any language out there only needs a cond or an if. Having both is a bit redundant. It's nice to have the pretty syntax. But if the language only has if expressions, then you can create a cond by having a bunch of nested ifs. It gets ugly, but it's possible. Similarly, if a language only has cond expressions, then you can create an if by just using conds that only have one branch and an else statement. So you only need one or the other, but there is a key difference between the two, and that is sequencing. So we discussed sequencing. We were talking about defining functions before. So sequencing is the idea that we can evaluate one expression after another, all in a singular context, so within one combination, for example, within the body of a function. But cond clauses will implicitly allow sequencing as well. So let's create another signum, or better yet, I'll just do it in this existing one. So we saw, or I mentioned at least, when using sequencing, really the only use of it is to have side effects, because the value of a sequence is still the value of the last expression in the sequence. So the only side effect that we really have any use for in our language, because we don't have mutable variables, the only useful side effect is printing. So let's do a display here. We'll say display positive if it's a positive number. We will display negative if it's a negative number, and otherwise we will display 0 if it's a 0 number. But we still want to return the actual value. So we want to display positive and return 1, display negative, return negative 1, or display 0 and return the value 0. Okay, so let's run our code again here, and let's try this out. So we'll say signum 3, because it's our third version, with the argument negative 3. And it says negative and then runs negative 1. So notice within one pairing here, we have our condition, and then not just one expression, but a sequence of expressions. And the value of that branch is the value of the last expression in that sequence. So if I happen to have +1, 1 in here, or a bunch of other numbers, in this case it will evaluate this. It'll get 2 out of it, but it won't do anything with that 2. It just essentially creates 1 + 1 is 2 and then throws it away. The value of this branch is the result there, the last expression. Run this again just to show that. We'll say signum 3 with the value 10, it says positive and 1, and this +1, 1 happened but was ignored. So I'm just going to delete it. Okay. So if we do that with if statements, on the other hand, it's a bit of an error. So let's just show you that in the REPL here. Say if x is greater than 0, we will display positive and then return 1. Now we want both of those to be the then part, so you might be tempted to maybe wrap these in a bracket. Just sort of a spoiler alert, this won't make sense because I'm definitely causing an error here. And then the alternative, or the else part here, will be display negative. We'll just forget about 0 for this example. Okay. So if we try to make an if statement where it does two things, so display positive and then 1, display negative and then negative 1, the error here is that this expression gets evaluated using the usual rules, right? If statements are special forms, and those have their own evaluation rules that say first evaluate this, if it's true, then evaluate this. But if we're evaluating this, we're doing that in the regular way, unless it happens to be some other special form. So in this case, it's just going to attempt to determine the value of the sub-expressions and apply the value of the procedure to its arguments. Now in this case, if we evaluate this, we do not get a procedure. Display doesn't have a value. It's only used for a side effect of displaying things to the screen. So if we have a combination where we have essentially a null at the front and then 1, we can't apply the null to the value 1 because that doesn't make sense. It's not a procedure. So if we try running this, error x undefined because we didn't actually create that variable. Let's just use something else here, like a 7. There's the error that I wanted to show you. Error expected an application, not a procedure. Or sorry, expected an application, but we didn't get a procedure. Okay. Now, if we do really want to use an if statement for whatever reason, but we also want sequencing, as say if we wanted to sort of shoehorn sequencing into places where Scheme doesn't provide it by default, we can use a special form called begin. I'm just going to bring that line back here. I'll bring this up here again. So if we want our code to do this and then this, we can put all of that into one big combination with the keyword begin at the front. Begin. So begin says, do a sequence of operations and return the value of the last expression. So begin essentially is already implicit in these combinations for cons and in the body of functions. It's just a way of saying, I would like a sequence to occur using the rules that we've learned for sequences. So it's going to evaluate each individual expression and then return the value of the last one. So if we run this, +1, it works fine. So special form begin says evaluate each one of these things and then return the value of the last one. All right, that is it for this video. We've covered conditionals in Scheme. It's also the end of this chapter, so in future videos we'll move on to new chapters and learn new and exciting things. Can't wait. I will see you in the next video.